Yep.
Yep. Sounds
Looks
nice
good.
and clear.
Okay, good. So thank you very much for this opportunity to speak to you guys. I'm especially grateful for this opportunity because my group, we don't really directly do quantum computing. So you know, quantum computing is a very hot field. And everyone is trying to connect what they do to it. But frankly speaking, you know, the type of research that I'll show, it does the connection is a little bit tenuous. But the general idea is that all type of computing ultimately involves manipulating some physical object, and oftentimes it is some physical object that is based on a material. And there are materials that have sort of been perfected for today's technologies, like our devices, our phones, our computers. There are materials that have been perfected for existing quantum computers. And then there are materials that might be utilized in future computing, quantum and otherwise. And that's what I'll be talking about today. So feel free to stop me if you have any questions. It's fine if I don't get through all the slides. I just want to emphasize more having a good discussion and having some learning going on rather than necessarily getting through all my slides. Okay, so with that out of the way, let's get into it. So the main takeaways from what I'm going to talk about are as follows. So new materials platforms are key for continued development of quantum technologies. And there's a fundamental connection between a material's electronic structure and its function. So how electrons move around in that material and what you can do with that material. And quantum materials represent a number of novel paradigms in materials' electronic structure and function that can be exploited in future technology. And I'll give a couple of examples about how this might work. So what I'll be discussing in this talk is sort of going to be a combination of research my group does and research my group does not do. So because of that, I want to begin with research that my group does do. So we have two experiments in my lab, RPES, which I'll discuss in this talk, and ultrafast optics, which I'll not discuss in this talk. And broadly speaking, we measure superconducting and topological quantum materials. The topological quantum materials is the one that I'll be touching on most heavily in this talk, but I'll also be talking about superconductors a little bit at the beginning, however, not the types that I study. So here are some of my current and recently departed group members. So on the RPES side of my group, Sudhir and Matt are third and second year grad students. On the ultrafast optics side, Adam Gross is a fourth year grad student. Antonio Rossi was a former postdoc that worked on the RPES side, and Enrique Martins was also a former postdoc that worked on a completely different area outside the scope of this slide. Alrighty. So the talk will proceed as follows. So I'll give a little bit of history, both a general discussion about how materials technology drives technology, and then discuss in a little more detail about superconducting materials, which is the basis of many existing qubits. So then I'll get into the main part of my talk about quantum materials. So I'll discuss what are quantum materials and how we measure how electrons move in quantum materials. So the measurement part is going to be applicable not just to quantum materials, but to all types of materials. And then I'll discuss two specific categories of quantum materials, topological insulators and Weil semimetals. All right, So just condensed matter physics in a nutshell. So we deal with crystalline solids. So a crystal in science means something different from the colloquial word. So it doesn't necessarily mean something that's sparkly and transparent. A crystal is defined as an object that has a regular arrangement of atoms. And pretty much, so even things that might not look like a crystal on the surface, like I don't know, the steel fork in your kitchen. If you take a little piece of it that is small enough, you will see a regular arrangement of atoms. So anyway, we can describe everything. So what's actually happening in a crystalline solid? We can enumerate all the things that are happening. So you have electrons moving around. You have nuclei vibrating in place. Sometimes you have atoms moving around too, but that's a little bit less common. And then for all the charged particles that are involved, you have various pairwise Coulomb interactions. So you have electron-electron Coulomb interactions, electron-nucleus Coulomb interactions, and nucleus-nucleus Coulomb interactions. So it's a fairly compact list of things that actually happen in a crystalline solid, but because there are so many particles in there of order 10 to the 23, there are endless possible materials phenomena with new states of matter, new phenomena and materials being discovered all the time. So human history can be described as a history of materials technology. So for example, in the distant past, we had the Bronze Age and the Iron Age, which represented humanity's ability to harness certain materials, namely for weapons. And then in the more recent past, we had a whole bunch of other materials coming to the fore with the Industrial Revolution and electrification and silicon-based electronics. And looking forward to the present and also the upcoming soon-to-be future, there is quantum computing technology and renewable energy, just to name a couple of directions where new materials can drive new technologies. So in this slide, I want to emphasize that the useful materials phenomena, especially in the modern era where we were interested in using materials to make electronic devices, the useful phenomena primarily originate from electrons. And the goal of condensed matter physics is to understand and harness these fundamental interactions. So the goal is understanding, and then applications come in the future after understanding happens typically. And sometimes the applications are a little bit surprising and unexpected. So with that, I'm going to get into the first topic that I want to discuss, and that is superconductors. So superconductors are utilized in many quantum computers. I guess it's debated by experts whether there are real quantum computers, but whatever is claimed to be a quantum computer, many of them utilize superconductors. So I want to talk a little bit about superconductors here. Okay, so superconductivity in a nutshell, it has two macroscopic observables. So that means big things that the chunk of superconductor does. So the first macroscopic observable is zero resistance. So this is not zero resistance for all temperatures, but at some temperature Tc, the resistance of a superconductor suddenly goes to zero. And then below Tc, the resistance is not really small, it's actually zero. And concomitant with this onset of zero resistance, a superconductor also expels its magnetic field. So this is called the Meissner effect. And most utilizations of superconductors take into account these macroscopic observables. So for example, MRI machines, they use the zero resistance property to be able to run a larger current through a superconducting wire in order to make a larger magnetic field. Other applications, and this is also what's utilized in the Large Hadron Collider. So other applications like this magnetic surfboard utilize the expulsion of a magnetic field. So the superconductor is inside this surfboard that the person is standing on. It's cooled by liquid nitrogen. That's the steam coming out of the top. And then it's running on a track of magnets. So, so that utilizes the expulsion of a magnetic field. So many purported quantum computers also use superconductors, but they don't directly utilize these macroscopic observables. They utilize sort of quantum properties of superconductivity that I'll come to in a few slides. Oops. Okay. So among superconductors, there are kind of two categories, or I would put them into two categories. So first of all, there are superconductors we understand. So in this context, understand means that there's sort of an established microscopic mechanism about why a certain material becomes superconducting, and that microscopic mechanism is agreed upon by the plurality of experiments and by the plurality of the research community. So among superconductors that we understand are many of the elements of the periodic table, such as niobium and aluminum. And these are the types of superconductors that are used in superconducting qubits. Then there is niobium titanium, which is one of the materials that's sort of a workhorse of superconducting electromagnets. And more recently, people have been able to make room temperature superconductors, actually, if they take something that contains a lot of hydrogen and compress it to pretty much the pressure of the inside of the Earth. If they do that, they can make a room temperature superconductor, and it happens to be the type of superconductor that we understand. So the other category is superconductors we don't understand. So this is the type of superconductor that my group studies that I won't be talking about today. But some examples of superconductors that we don't understand are cuprate high temperature superconductors, iron-based high temperature superconductors, or heavy fermion superconductors. So they look like black rocks, silver rocks, and gold rocks. But also in this category, which I don't have on this slide, is what are called topological superconductors, which may be the basis of fault-tolerant qubits in the future. All right, so for superconductors that we do understand, there are sort of two, so first of all, the theory that explained why they became superconducting was put forth by Bardeen, Cooper, and Schrieffer in 1957. They received a Nobel Prize for it in the 70s. And there are a couple of aspects of this theory that I want to highlight. So first of all, in a superconductor, the charge carrier unit is not a single pair of not a single electron, but it is a pair of electrons called a Cooper pair. Typically, it's a singlet pair consisting of one spin up and one spin down electron. It doesn't have to be, however. So in addition to the formation of these Cooper pairs, which is mediated by atomic vibrations of the atoms in the crystal, so the formation of these Cooper pairs is one aspect of superconductivity, but the other aspect of superconductivity is phase coherence. So you not only need Cooper pairs, but you need the Cooper pairs entering into a single quantum ground state and becoming coherent with one another. So this coherence is what is utilized in superconducting qubits ultimately. So the wave function of a superconductor can roughly be written as some amplitude times some complex exponential, which contains a phase. So the magnitude, this delta parameter, that is something that depends on a material. So if you're talking about aluminum, if you're talking about niobium, if you're talking about a different type of superconductor, you will, in general, have a different magnitude. Generally, the higher the onset temperature of superconductivity, the larger this will be. And this magnitude also represents the energy that it takes to break apart a Cooper pair. The phase is something that is sort of spontaneously chosen upon cooling. And I'll explain that a little bit more when I describe this drawing here. So in principle, the magnitude or the phase might depend on direction. So whether an electron is moving this way, that way, whatever way, it could depend on that. In superconductors we understand, typically it does not. And another thing to note is that if you have a gradient of the phase, so if you have one phase in one part of your system, another phase in another part, that generally corresponds to current. Okay, so let me contextualize all of this with this drawing here, which illustrates a Josephson junction. So Josephson junction is where you have a superconductor that is abbreviated by some non-superconducting material, typically an insulator of some sort. So in this drawing, you have a superconductor on the left, which has the subscript L, superconductor on the right, which is called, which has the subscript R, and when this chunk, this device, is cooled down below the superconducting transition temperature, the phase on the left side and the phase on the right side are sort of spontaneously chosen without, it's not going to be the same every time. So in general, you'll have some phase difference across this, this barrier, and you can have a current flowing, and you can also transfer Cooper pairs from one of the superconductors to the other superconductor across this insulating barrier. And this is called quantum tunneling. So Josephson junctions are the basis of many superconducting devices, including superconducting qubits. So this is well outside of my expertise, but I just want to draw a couple of illustrations. So the general idea behind all of the applications of Josephson junctions is when you have a loop of superconductor, then the flux inside the loop is quantized. So magnetic flux is given by magnetic field times area. And in a superconductor, because of the quantum coherent nature of the superconducting state, the flux that threads that loop is quantized. The quantum of magnetic flux is given by this expression. It's just h divided by 2e, so it's just a function of fundamental constants. And this turns out to be a teeny tiny magnetic flux. And this is, so although flux is not in units of energy, it can be made into units of energy with proper multiplication of constants and geometric factors. And this small energy scale is essentially the reason why quantum computers need to be cooled down to dilution fridge temperatures, even though the superconducting transition temperature might be 1 Kelvin or 3 Kelvin or 7 Kelvin. So anyway, so the RF squid is the type of device that's usually used in superconducting qubits. It has one Josephson junction in the loop and other circuit elements that I'm completely omitting here. And DC squid is another device that can be constructed using a Josephson junction. And it has two Josephson junctions in the superconducting loop. And DC squid also has a number of applications. So it's used in magnetic sensors, including ones that are in kind of commercial devices that some of my colleagues have in their lab. And formerly, it was also used for the definition of a volt, although now they've redone the SI units a little bit, so that's not the case anymore. Okay, so I want to close the discussion about superconductors we understand with sort of a history lesson. So superconductivity was discovered in 1911. It was discovered in Mercury, and it was not fully understood until 1957. So we should give humanity the benefit of the doubt there, because during those intervening 40-something years, they also figured out quantum mechanics and solid state physics and all of that. But in any case, there was a huge gap between discovery and understanding for superconductors. And in the same time period that the microscopic mechanism of superconductivity, at least for superconductors we understand, was put forth, that was also where the scientific basis for many of the devices that take use of superconductors' quantum nature was put forth. So, for example, specifically, quantum tunneling was measured in the 60s, and the Josephson effect was predicted in the 60s as well. So fast forward another 30 years, and then it wasn't until the 90s that people really started to take seriously the idea of making qubits, making quantum computers out of superconductors. So in the 90s, that's when the idea started to percolate. And that's also when, towards the end of the decade, when there was the first demonstration of a superconducting qubit. And then 20 years after that, that was when the commercially available purported quantum computers, specifically D-Wave, started to be available. So all of this is to demonstrate how the path between fundamental science and applications is long and surprising. Certainly, even in the 60s, when people understood all the ingredients that now make up superconducting quantum computers, that application was still not considered at the time. So still, although there are purported quantum computers, there are still challenges in this field. So a known challenge is essentially that these devices are susceptible to noise and errors, which are difficult to correct in a quantum context. So one of the ongoing challenges in this field is creating fault-tolerant quantum computers, which may require a new materials paradigm. And there are a variety of challenges related to both superconductivity and quantum computing that new materials can address. I'm about to move on to the next portion of what I want to discuss. Are there any questions at this point before I get there?
The explanation on the Josephson Junction is much appreciated. I think in prior workshops, the organization has talked about ion traps and other, I think we did diamond vacancy centers as well, but it's a particularly tricky thing. So the explanation you gave is much appreciated.
Thank you. All right, if there aren't questions, then I'll move on. And at this point, I'm going to switch gears quite a bit and talk about quantum materials. So the idea here is that we want to replicate, if we can, what was done with superconductivity. So we want to find new materials that have new interesting phenomena that at this point we know that they're unusual and interesting, and maybe in the future, hopefully not 100 years in the future, there will be some applications for some subset of those materials. So quantum materials, it's kind of a sociological term as much as a physics term, but generally speaking, quantum materials are characterized by the theme of emergence. So that is the idea that more is different, and the properties of many electrons in a crystalline solid cannot always be predicted from understanding the properties of just one electron. So among quantum materials, there are sort of two categories and some materials that also span both categories. So the two categories are, first of all, materials that have strong electronic correlations. So the idea there is that you have electrons in a crystalline solid, and electrons Coulomb repel each other. So dealing with these Coulomb repulsions is, as far as theoretically, numerically, what have you, is very challenging because these are pairwise interactions between every electron and every other electron. And in a lot of solid state physics from the 20th century, these correlations are ignored. So the solid state physics that we use, for example, to understand the silicon in all our devices, it mostly ignores correlations between electrons. But in quantum materials, these interactions cannot be ignored. Another aspect of quantum materials is that some of them have some sort of topological order. So there's some geometry of their many-body wave function that yields unusual electronic properties. So let me, to summarize kind of the connection between quantum materials and quantum computers before I veer off in a completely different direction, let me just summarize it here. So there are kind of two approaches. So one approach is that quantum computers, ones that we have now, ones that we might have in the future, they may be used to explain the behavior of quantum materials. So an example of this is high temperature superconductors, which are materials that have been known to be superconducting for almost 40 years, but we still don't understand why they become superconducting. And one of the challenges is the strong electronic correlations. And it is thought that maybe quantum computers can help solve this longstanding challenge. And this is just one example of a longstanding problem that people think that quantum computers might be able to properly model. So that's one approach. But the other approach is that quantum materials may be the basis for novel computing paradigms, including quantum computing paradigms. So examples of this include quantum sensing, spintronics, I left off a comma there, sorry, fault-tolerant quantum computing as well. And this is where topological quantum materials might play a role. So before I get there, let me discuss a little bit about how electrons move in crystalline solids and what we can learn from it. So to do that, I want to just harken back to classical objects. So like if you throw a ball, it has some kinetic energy, which can be written as the momentum squared divided by 2 times the mass. And a dispersion relation is basically energy as a function of momentum. So this expression for kinetic energy that I wrote right here, that's applicable to planets and balls that you throw, that's an example of a dispersion relation. So you can also have dispersion relations for, electrons in a solid. So you can have simple dispersion relations, such as this case here, where it's just parabolic. So it looks just like a classical dispersion relation. And it's what you get just by solving the Schrodinger equation without any external forces. So you can have very simple dispersion relations, energy versus momentum in a crystalline solid, or you can have more complicated dispersion relations, not necessarily more complicated, but just not this quadratic dependence. So dispersion relations are something that can be measured, and the technique to measure them is one that my group does. It's called angle resolved photoemission spectroscopy, or ARPES. And this is a technique that's based on the photoelectric effect. So the idea is you shine light on a material and you eject electrons, and it turns out that these electrons are still carrying information about how they were moving back inside the crystalline solid. So that is governed by 2 relatively simple equations. So one thing that we measure in ARPES is the kinetic energy, which can be related by things that we know, the photon energy of light we use, the work function. And the other quantity that's measured is the emission angle, so the angle with which the electron flies off from the crystal. And that can be connected to the momentum that the electron had inside the crystal. So basically, ARPES measures energy versus momentum, which is a dispersion relation. So this is a technique that can fully describe how electrons move in crystalline solid. So what we can learn from dispersion relations is things like electron velocity, electrons' response to electromagnetic fields, electrons' effective mass, and there are many macroscopic things that originate from dispersion relations. And I'll try to give a couple of examples of that as I go on. So let me quantify some of these statements that I made. So ARPAs can measure electrons' velocity, and I'm illustrating this using some of our group's data on high temperature superconductors. So as a reminder, if you have a classical object, the kinetic energy goes as momentum squared. And then if you take the derivative of kinetic energy with respect to momentum, you get P divided by M, which is velocity. So there's a relation between slope and velocity. So similar for electronic dispersion relations, the slope, when you have energy plotted as a function of momentum, gives you velocity. So for example, in these data here, the highest slope is over here. So electrons move fast when they are at this coordinate of energy and momentum. They move slower at these coordinates, and they move slowest at these coordinates. So another thing that ARPAs can measure that can also be understood with a classical analog is effective mass. So for classical objects, we have this equation that I keep showing, and the second derivative of energy with respect to momentum gives 1 over the mass. So we have this relationship between curvature and inverse mass. And the same idea holds for electronic dispersion relations. So the second derivative of energy with respect to momentum is inversely proportional to effective mass. So in crystalline solids, electrons, they can behave in weird ways. So sometimes they can behave like light, and we'll be seeing a lot of that in the coming slides, but sometimes they can behave like they're really heavy. And the case where they behave like they're really heavy, these are called heavy fermion materials. And basically that's when you have the energy versus momentum curve being like these dots in panel B and panel D, so almost horizontal. So that corresponds to a large effective mass. But we can also have the case of zero effective mass. Okay, so more broadly, ARPAS measures a wide variety of emergent materials phenomena. So sometimes it can measure the free electron-like energy versus momentum behavior in simple metals. Some materials have many bands, many energy and momentum states that electrons can exist in, and it can measure that. For superconducting gaps, that's the energy to break apart a Cooper pair. ARPAS can measure that, and it can do that in a momentum resolved manner. And it can also distinguish surface and bulk states, which will be important for the materials that I'll show in coming slides. It can also measure what's called electron-phonon coupling. So basically, electrons interacting with the lattice vibrations, which is relevant to the mechanism of superconductivity and superconductors that we do understand. So that is the technique, and I'll be talking about sort of quantum materials as being in contrast to kind of ordinary materials. So I want to make that contrast more quantitative. So what do we expect from ordinary materials, contrasting that what we often see in quantum materials? So in ordinary materials, the energy versus momentum relation of electrons is usually pretty close to being free electron-like. So usually it's close to a parabola. Additionally, you can have, so in a crystalline solid, you have the bulk, which is sort of the deep interior, and then you have the surface. And sometimes the surface is different from the bulk because if you think about in the bulk, either an atom or electron, whoever's point of view you want to think of, it sees sort of the same thing, repeating atom over and over towards infinity. But when you get to the surface, you break that symmetry. Suddenly, at the surface, if you look down, you see repeating atoms over and over. You look up, you see nothing. So that's you can get different electronic structures at the surface. But in ordinary materials, these surface states are often easily destroyed. So, for example, a small amount of disorder, high temperature can just kill whatever surface state you have. And finally, in ordinary materials, electrons typically scatter off all kinds of impurities, and that is what causes finite resistance in most metals. So that is the case for ordinary materials, and this is contrasted with quantum materials. So what I'm going to put on this slide is not going to be statements that are true for every quantum material, but these statements are going to hold for some quantum materials, and for many of them, in fact. So one aspect of quantum materials that happens a lot is that at least some of the electrons behave light-like. So for light, energy is equal to momentum times c, or writing down in terms of quantum mechanical momentum, h bar k. So, sometimes in quantum materials, you can have electrons behaving like light. So that is to say, those materials are sort of like little universes that have a speed of light that's different, always smaller than the regular speed of light, but nevertheless, electrons in many ways in those materials behave like light-like particles. So that's one aspect. Sometimes in some quantum materials, you can have either robust or unusual surface states. So robust means that they are somehow protected by something inherent about the crystal. And if you raise the temperature or dump impurities on the surface, you won't destroy the surface state. And finally, some types of scattering can be disallowed. So specifically, the materials that I'll be discussing in the coming slides, this sort of backscattering, where you have an electron going one way, it sees an impurity and oops, it bounces all the way back. These types of scattering events are disallowed in some types of quantum materials. All right, so that is, a little bit more preliminary information. Okay, so in the coming slides, I'll also be discussing some terminology that I want to clarify here. So metals versus insulators versus semiconductors versus semi-metals. Okay, so this view graph summarizes all those differences. And let me start by, E sub F is called the Fermi energy, and it represents the highest energy occupied state. So for an insulator, the Fermi energy lies inside the band gap. The band gap exists between the valence band and the conduction band, and the band gap represents sort of forbidden states. So these are states that electrons cannot have. Electrons can live in the valence band, they can live in the conduction band, but they can't live in the band gap. So an insulator is characterized by a large band gap, typically larger than visible light. So for that reason, many insulators, such as this glass dirty cup that I used to have coffee in earlier, they are transparent because the band gap is larger than visible light. So semiconductors, and ignore the p-type, n-type distinction here. Semiconductors are for most intents and purposes, they are exactly the same as an insulator. So from my perspective, no difference. So like an insulator, semiconductor has a filled valence band and an empty conduction band. The difference between a semiconductor and an insulator is that a semiconductor has a smaller band gap, typically below the frequency of visible light. So if you look at a chunk of silicon, it'll look sort of gray, and the reason that it's not transparent is because it has a smaller band gap than SiO2, which makes up my dirty coffee cup. Okay, so a semi-metal is when you have your valence band and conduction band starting to touch. And then finally, for a metal, the concept of valence and conduction band aren't really a thing. And a metal just has a partially filled band where the Fermi energy is somewhere inside the band, not inside the band gap. Okay, so that's just some terminology. And then let's get into the, oops, okay. So I guess before I get into topological insulators, are there any questions? All right, if no questions right now, then I'll keep going. So topological insulators are kind of a paradigm quantum material. They really started the field of quantum materials. So many materials that are now called quantum materials were studied extensively before topological insulators came along, but topological insulators introduced this ingredient of topology into sort of categorization of materials. So topological insulators, I have an asterisk because they're technically semiconductors, but semiconductors and insulators are the same thing, so whatever. Most of them that have been discovered, at least three-dimensional ones, they have sort of this general crystal structure. They are materials such as bismuth-2, selenium-3, bismuth-2, tellurium-3. So they have heavy atoms, so bismuth or antimony, typically, and then they have some chalcogen, selenium or tellurium, sometimes sulfur. So these materials, so they sort of gained popularity in a new field about 12 or 13 years ago. But they were actually studied for a long time in the context of thermoelectrics. So this is what they look like. They look like little silver rocks. And these are materials that have been studied for decades, since the 50s. And they were well known to be thermoelectric materials. Those are materials where you can make a temperature gradient across the material to create a voltage gradient, or do it the other way, apply a voltage to create a temperature gradient. And thermoelectrics are utilized in solid state cooling. So for example, what's it called? This cooler that you plug into, well, if you want it to work, you should probably plug it into the wall rather than your car cigarette lighter. But anyway, these types of cooling devices that are thermoelectric, they almost certainly use materials in this category, typically bismuth telluride. So this silver rock, it is what's called a three-dimensional topological insulator, meaning it is insulating or semiconducting inside a three-dimensional bulk, and then it has a metallic surface state sort of that's two-dimensional that wraps it up like a present. The same idea or the same type of phenomena can exist one dimension lower. So in two-dimensional topological insulators, you have a insulating interior in a sheet, and then the edges, the one-dimensional edges, are what is conductive. The elephant in the room is what is topological about them. And so what is topological about them is the geometry of their many-body wave function. And it's a little bit outside the scope of the talk, but the idea is that for sort of geometric objects, there you can sort of classify them into certain topological classes, and then you can deform those objects and still have them be in the same class. So for example, this torus with one hole, it can be deformed without making any cuts into a coffee cup. This double torus thing, without making any cuts, can be deformed into a pair of pants, and then this triple torus can be deformed into a shirt, just as examples. So anyway, these are called topological insulators, and what they are characterized by is certain specific electronic properties that I'll come to on the next slide. So the electronic properties that define and characterize topological insulators are as follows. So the bulk or interior, so the three-dimensional bulk for a 3D TI, or the two-dimensional interior for a 2D TI, it is an insulator or semiconductor. And then you have something different happening either on the surface or on the edges, depending which dimensions. So one thing that happens is you have light-like electrons. So the energy versus momentum. So this graph doesn't have axes, but the y-axis is energy. The x-axis is two axes of momentum, and it's linear. So there is light like electronic dispersion of states at the surface. And those surface states also have spin momentum locking. So that means that a spin or an electron rather that's moving in a specific direction, it has a specific associated spin. And finally, an important aspect of these materials is that this electronic structure of the surface state is difficult to destroy. So if you dump non-magnetic impurities on it, nothing will happen. If you raise the temperature, nothing will happen. It's a very robust surface state. The only way to really kill it is to add magnetism, such as magnetic impurities or a magnetic field. And importantly, these unusual electronic structures of topological insulators are realized at room temperature and zero magnetic field. So very ambient conditions. All right. So, three-dimensional topological insulators and two-dimensional topological insulators, there are many examples of them. So one example is bismuth selenide, as I mentioned, and here is some ARPES spectra of it measured in my group. It's a very easy material to do ARPES experiments on it, actually, and it's an example of a material that matches pretty closely to this ideal in many ways, other than you have to work harder than we did here to actually make it be insulating. But anyway, all of the features that are in the sketch, the bulk conduction band, the bulk valence band, the Dirac-like surface state, they're all readily observed experimentally. All right, so what can you do with this unique electronic structure? So I'm going to talk about sort of applications that have been thought of already, although not necessarily implemented into devices. But that doesn't mean that what ends up happening in the future might not be completely different. It probably will. So one thing that you can do is you can detect infrared circularly polarized light. So with light, what you can do is you can promote an electron from from the lower part of this surface band to the upper part of the surface band. However, when you do that, it needs to flip its spin. And generally, light will not cause a spin to flip unless it's circularly polarized light. So these materials can be used as detectors that are especially tuned to circularly polarized light. So another aspect that they can be utilized in is spintronics. So that comes from spin momentum locking. Electrons moving in one direction have a specific spin. So you have sort of an automatic way to use a known spin state for whatever you want to do. So here's the spintronic sketch. Another application is dissipationless edge currents. So this is an application that's more achievable in a two-dimensional topological insulator, but again, this originates from spin momentum locking. So if an electron moving in a specific direction needs to have a specific spin, it cannot scatter backwards because electrons moving in the backwards direction have the opposite spin. So it can, if it meets a non-magnetic impurity, then it just has to suck it up and go around it. And this is pretty much true in two-dimensional topological insulators. In three-dimensional topological insulators, scattering is reduced but not completely forbidden because the electrons can scatter into other angles other than completely backwards. Another application that can be done, which I'll talk about on the next slide, is making it superconducting. And this is the basis or one way to produce potential materials for topological quantum computing. And another thing that can be done is turning it on and off. So for example, in this two-dimensional TI, you have your dissipationless current flowing on the edge, and if you can find a way, in some cases, to turn it off. So you have a very good conductor on the edge, and suddenly you don't. Okay, so let me go into a little bit more detail about some of these applications. So first of all, making it superconducting. And this is one way towards topological and fault-tolerant quantum computing. And if you're interested in learning more about this, I recommend that you check out this review paper, which I think was pretty readable. So the general idea behind this is something that is true for many superconductors. So if you take a superconductor and you put it up against something that's not a superconductor, like an ordinary metal, the superconducting order parameter can penetrate into the normal metal and make at least a thin layer of the normal metal become a superconductor. So this is called the proximity effect. And the nature of the proximity effect depends on what is happening in the normal metal. So if you have a superconductor interfaced with a normal, like a typical ordinary metal, then whatever proximity effect you have will usually be relatively conventional. But if you stick your superconductor onto a weird metal, like the surface state of a topological insulator, then you can get a weird proximatized superconductor. So this weird proximatized superconductor can then be used to produce Majorana fermions. So a Majorana fermion is a fermion, it's a particle, which is its own antiparticle, and it's sort of half of a fermion. So two Majorana fermions must combine to form a fermionic state. And they are realized actually when superconductivity is abbreviated. So for example, if you have a two-dimensional TI with a one-dimensional metal at the boundary, and then you make that one-dimensional metal superconducting, then in order to potentially create Majorana fermions, you need to sort of kill superconductivity on one segment. So you have sort of a wire with a beginning and an end, and the Majorana fermions or Majorana zero modes can form at the end of this wire. And the idea behind topological quantum computing is that you can use the exchange or braiding of these Majorana fermions for computing paradigms that have sort of an enhanced stability against decoherence. So this is not exactly the topic of my research other than the topological insulator part, but I will say that as far as where the community is at this point in this regard, so there have been recent controversies, a prominent retraction where they were trying to create Majorana fermions using a slightly different approach. So I'm not going to touch on that here, but basically there are examples allegedly of proximatizing this edge state, and also examples of allegedly Majorana fermions. Braiding and manipulating these particles, not so much. All right, so another approach is that one can turn off the edge states. So you have an edge current that has limited scattering and spin momentum locking. So this is sort of something that let's say this is your on state, and then you can use temperature, voltage, light, magnetic field, depending on the material, to switch that into an ordinary insulator or semiconductor. So this is something that which my group's research touches on that I'll get to in the coming slides with a slightly different topological quantum material. And I'll go through this very quickly because we're coming up on the 6 o'clock hour. But before I get there, are there any questions?
For the topological,
go ahead, go first.
Would you go back to the 3D topological case where you have the that one?
Yeah.
So is the valence band and the conduction band, are those both different materials, or is it from one bulk material and it just creates the structure?
Yeah, so this is one single material, and that's one of the I guess the attractive things about it. It's really just a single material where if you just consider the valence and the conduction band, you know, that's what you have in an ordinary semiconductor. But what's special about a topological insulator is that you have this this unusual surface state that exists only at the surface, or if it's in a lower dimension, it's along the boundary, it only exists at the surface in that same material.
And this represents 1 qubit or I guess
So-
like one.
This is not a qubit. It's just a sort of electronic structure of a material that is a little bit unusual. And if you want to make a qubit out of it, then you have to make it superconducting, and then you have to kill superconductivity in some local region, and then you have to basically if the correct emergent particle appears there, you have to move those particles around each other. So it's sort of a long journey from a material to a qubit at this point.
Okay, yeah, I was a little confused because I saw a previous picture and you had a spin up and a spin down that was overlaid on top of this topological structure. So I was just wanting some clarification on that. Thank you.
Was there another question?
Yeah, I had a question about the massless electrons.
Yeah.
Like, at what point does it go from like that, I guess, whale fermion to a Dirac fermion? How do you like see that in the lab?
Okay, so maybe I can explain that in the next section where I'll be discussing Weil fermions or Weil semi-metals. So I'll be sure to emphasize that point. And is there a question or in the chat? All right. So yeah, let me go through the next part, and please ask me again if I don't answer it at that point. Okay, so yeah, let me move on to Weil semi-metals, and I'll discuss this quickly. So topological insulators are sort of one type of topological material, one type of material that's sort of characterized by a specific bulk electronic structure, a specific surface electronic structure. So there are many other topological materials, and Weil semi-metals are one category. So a Weil semi-metal, so the next two slides will sort of try to explain what it is. It's a little bit complicated. So like the topological insulator, it has distinct bulk structure from the surface. So in the bulk, it has what are called Weil nodes. I wish I didn't use the word Dirac like here, but basically it is sort of this picture where you have kind of a conical structure, except it's a four-dimensional object. So instead of just Kx and Ky, you would also have Kz and energy. So you would have this sort of energy versus momentum being plotted in 4 dimensions. So a 3-dimensional object, but there's the energy axis as well. So in a Dirac material or an ordinary material, at every state, at every Kx, Ky, Kz energy, you would have 2 states where electrons can live, one spin up and one spin down. But for the case of a Weil semi-metal, it's half of that. So you would only have one at each state. So that's what the bulk is doing. And on the surface, there's a very unusual structure called a Fermi arc, which is also a spin momentum locked structure, but it's kind of this bizarre thing that has, that's like not a closed contour, but an arc. So most features in crystalline solids in momentum space are closed features. Fermi arcs are very bizarre and seen only in limited contexts. So Weil semi-metals require the breaking of some symmetries. So for example, a Dirac semi-metal, that is this picture in 4 dimensions exactly. So Kx, Ky, Kz, and energy. So then then you break that up into pieces, either by breaking inversion symmetry, where you end up with 4 Weil nodes, 2 of each chirality, or you can break time reversal symmetry and only get 2 Weil nodes. So an example of a material that breaks inversion symmetry is tantalum archive. So if you look at this yellow arsenic atom and go through the center and hit the same point in the unit cell, there's no yellow arsenic atom. And sorry, I have a typo here. This is supposed to be time reversal symmetry breaking. This is a material that is magnetic. So in magnetic Weil semimetals, you break time reversal symmetry, and that's another way of breaking up a direct dispersion into a Weil dispersion. So a Weil semimetal and also a direct semimetal, graphene as well. So these are all examples of sort of particles that have been predicted from particle physics and then show up in a condensed matter context. Oftentimes, you can get particles that are realized in materials that are not seen in free space or have not yet been seen in free space. So anyway, this is the last slide that I'm going to show. But in my group, we have done a lot of recent work pursuing switching in Weil semimetals. So because they rely on certain symmetries, sometimes these symmetries can be turned on and off. So one material that we have looked at is tungsten ditelluride, which is an example of an inversion symmetry breaking Weil semimetal. And this inversion symmetry breaking can be alleviated by moving the crystallographic, it's a layered material, and it can be alleviated by moving the planes. Another system that we've been looking at is Cobalt Tin Sulfide, which is a magnet where the magnetism supports the Weil semimetal, and we can raise temperature to kill the magnetism and also to understand how the Weil semimetal state emerges to begin with. And this is really important to set the stage for being able to switch these materials using sort of non-thermal perturbations such as a voltage or light. So yeah, so that's all that I wanted to say. So the conclusion is just that the take-home message is that computing technology is often built using materials, and quantum materials are examples of materials that are currently in the realm of basic research, but they could be the basis of new computing paradigms in the future, not only strictly quantum computing, but spintronics, optoelectronics, or whatever other ways of doing computing that we come up with in the future. So yeah, thank you guys for the invitation, and I'm happy to answer any more questions that you have.
I did have one question, although this is more a bit of a controversy that it seems to have arisen maybe several months ago with regards to the existence of the Majorana fermion and the whole. I'm aware it's quite a contested field, and I wanted to ask what your stance on it is. Like, was it did it seem like was it handled properly in a sense, or do you feel like there really was some malice going on, or?
Yeah, thanks for asking that, and for also phrasing the question in the way that you did. So just to be clear, that research is quite a bit out of my field. So we're doing topological quantum computing, but not using topological insulators. The actual materials platform was basically a superconductor interfaced with essentially an ordinary semiconductor with sufficient spin orbit interactions. So anyway, I don't have a dog in that fight, but from what I could see, it wasn't really an example of malice. It was sort of being a little bit careless with analyzing and plotting the data, and this, I don't want to blame the authors for what they did, because it's sort of a scenario where you have sort of some theory that almost matches the experiment. And I think many scientists, particularly junior ones, might be a little bit less critical of their data in the context where it almost matches with the theory. So, it's an example of a mistake that happened. They were a little bit careless, but I don't think it should sort of reflect poorly on the researchers. So it wasn't really an example with with where I could see any evidence of malice or actual fabrication of data. So that's one side of things. But the other side of the issue is sort of how it was, I guess, treated in the media, which was a little bit confusing to me, being from the material side of things. So in the media, it was, you would get the impression that the results of this retracted paper was that, Majorana fermions cannot be created in a solid state context, and topological quantum computing is over. So the retraction, it was bad news for Microsoft, but there are many, many, many ways to get to potentially get Majorana fermions. There are sort of many, I don't want to quantify it, but there are a lot of different proposals. There's plan A, plan B, through the entire alphabet. There are many potential materials platforms where Majorana fermions might be realized. Other materials platforms, other than the specific architecture that Microsoft was pursuing, where it might have been realized. So it's certainly not the death of this approach. It does illustrate that this approach might still be more in the realm of basic science rather than applications right now.
Got it. Thank you so much for that, the information, because I've just seen it, all over the internet and LinkedIn, and different professionals have different takes on it, especially considering that the large chunk of this research was funded by Microsoft, and they do have a great incentive to prove after several years that they have, a feasible technology, which I think is part of the underlying concern. But
exactly.
All right, I'll open the floor to if anyone else has any questions.
So I was just looking at some of your previous papers, Dr. Vishik, and I was looking at one on like the electron phonon coupling and how you would kind of like measure that or use that. Would there ever be a possibility where you could map the phonon coupling effectively enough such that you could do a superconductive Cooper pair-like interaction, but model it on a material that's not necessarily a superconductor? You could like pull out those phonon interactions?
So I'm not sure I exactly understand your question, but electron phonon coupling is something that happens in a lot of different materials, not just superconductors. So it happens in every material. So if let's say every metal, when you're running a current through a wire at room temperature, what is primarily causing it to be resistive is going to be electrons scattering off of phonons. So it's something that happens in a lot of materials. For superconductors that we understand, so for things like aluminum, it is that interaction between electrons and lattice vibrations, phonons, that actually causes superconductivity. But there are other superconductors where electron phonon coupling might not be the initial cause of superconductivity, but it can be a mechanism of raising or lowering what the superconducting transition is. So I don't know if I answered your question, but if not, maybe you could ask it again.
Yeah, I think so. I mean, mainly I was just asking if say for information science particularly, right? Wherein like if you could understand the phonons that are interacting in that system, then would you need a superconductor? Because then you just have some sort of error correcting code that essentially takes out the effect of the phonons, but then that would be really difficult to be able to understand fully, for given the heat and other things that could go on in a material, right?
Yeah, so okay, so in the context of present day superconducting qubits, they are operated at such exceedingly low temperatures that phonons are not there aren't a lot of activated phonons that can scatter. So it's at such low temperatures that typically one doesn't think of lattice vibrations interfering with behavior.
Okay, I see what you mean. Thank you for explaining that.
Okay, I think I can clarify what Samarth was trying to describe there.
Okay.
I think he was asking about some analog of some type of superfluid system that was coupled with a quasi-particle, analogous to how an electronic superconductor could be coupled with a phonon. But I think he was just asking about some other type of superfluid system.
Oh, some other superfluid system that's
Yeah,
not
coupled
the.
Yeah, and coupled with like just some other quasi-particle, not necessarily a phonon. He was just asking about, are there other types of analogous coupling behavior, something like that?
Okay, so yeah, to answer that, yes, electrons can couple with other excitations. So if considering magnetic systems, they have elementary excitations that are sometimes very similar to phonons, and electrons can couple to those as well, as one example.
Okay, thanks for the clarification, Craig. Yeah, that's kind of looking at, because I was like, maybe if like you could look at, I don't know, like a nitrogen vacancy based system for modeling something like another superfluid system, that would be pretty interesting.
Oh yeah, you mean the idea of using sort of quantum computers to model sort of, for example, superconductors that we don't understand?
Yeah.
Yeah.
Okay, yeah,
Superfluid.
absolutely. So this is definitely something that I don't know if it's possible yet, but it's certainly one of the hopes for the future, using quantum computers, whatever their physical basis might be, to solve long-term challenges in solid-state physics.
So then if that was sorry, just like one last follow up on that. So if that's kind of like potentially a goal for modeling, then would a fault tolerant computer be necessarily something that would help in that process? Wouldn't that just get rid of like all potential phonon interactions then, if you had a fault tolerant computer completely?
Yeah, so yeah, I don't have a good answer to that that comes from my own mind, but what I've heard from other people in the context of the controversy and retraction we were discussing earlier is that, possibly what could end up happening is that instead of us reaching fault tolerant quantum computing, there's just, like a way to go around it with other approaches to quantum computing. So, it's still not known sort of what materials technology will ultimately win the race, or maybe there's going to be kind of different applications where you might use one versus the other. So for example, in semiconductors, most of our devices or all our devices pretty much are silicon based, but there are other semiconductors. So wherever you have a light emitting diode, that is a semiconductor that is not silicon, that is some direct band gap semiconductor. So even for semiconductor technology, there's sort of different material solutions for different problems.
Right. Yeah, I was in Dr. Woodall's class and he was really mad at saying like, man, silicon was not the right choice. It actually was not the right material, but because of how cheap it was, it ended up being the most manufactured and modified. So yeah, definitely some interesting stuff.
Yeah.
All right. Anyone else have any other questions?
Okay, well, if nobody else has any other questions, or I don't know, Professor, if you want to say any last remarks before I stop the recording.
Nope, I'm done. Thank you guys for your really good questions and your attention.